Our next presenter, Kelvin Wang, and presenting on thermoacoustic sound generation using the flexible encapsulated carbon nanotube sheets. Okay, go ahead.
My name is Wang, and I work with Dr. Ali in developing a flexible encapsulated carbon nanotube speaker. And so basically, in a normal speaker or sound generation device, the sound waves are created by a vibrating medium, and they create pressure waves that we hear as sound. But thermoacoustic devices, they use heat to induce sound waves, so there are no moving parts or anything. And thermoacoustic devices act as heat engines. Basically, they use heat to do mechanical work. And in this case, it's generating sound waves. So carbon nanotubes as the heating element. If you run a AC sinusoidal current through carbon nanotubes, because of their nano size and because they have the ability to heat up and cool down very rapidly, it'll generate a sound wave. The multi-wall nanotube sheet that we use is about 20 microns thick. And in this equation for sound pressure in a closed system, you can see the main factors are the thermodifusivity of the surrounding gas, temperature, pressure, volume of the container, and also the frequency of the applied signal. And you can note that this equation predicts increasing frequency leads to decreased sound pressure. So these basic equations, the first one is the Carnot efficiency, which depicts the theoretical maximum thermal efficiency of a heat engine. And basically, it depends on the temperature gradient. It's 1 minus the colder temperature over the hotter temperature, and the farther apart these two temperatures are, the higher maximal efficiency that can be attained. The second one is the ideal gas law, since the device we're making is encapsulated. The volume is going to be fixed, so as are N and R. And you have a law for the electrical current that we will be applying to the device. And also, this is the sound pressure for an open system from which the sound pressure for a closed system can be derived. So for our experimental setup, we have a sine-shaped signal of 45 volts generated by the generator, and it's sent to the amplifier, which amplifies it, and then sends it to the encapsulated carbon nanotube sheet. The microphone picks up the sound that is generated and sends it to the preamplifier, which amplifies the picked up sound, and it also converts it to an electrical signal. You can choose low pass and high pass filters in the preamplifier to clarify the signal, and then basically all of this is sent to the oscilloscope where we can visualize the input and receive signals. And we measured the peak-to-peak voltage of the received signal in millivolts. So preparing the device, basically we took sheets of aluminum foil and stainless steel, and we applied pressure to them to make these bubbles, and basically they look like this. And then on the edges we applied thermal tape to insulate them from the electrodes so the device won't short circuit. And also the sheets of metal were also covered with polyvinyl alcohol to insulate. And then basically we pulled a multi-wall nanotube sheet over the electrodes and sealed the edges to create an airtight device. And this is what they actually look like. They're approximately 3 by 4 centimeters. And on the top right, that was the very first one that we created. It's actually 20 millimeter encapsulated bubbles. And then, so this is the first device, and you can see it's fairly linear, and then it decreases after some resonance at around 10 kilohertz. And then these are the smaller devices that we did with 5mm capsules. There's resonance around 6 kilohertz, and all of these were done with an input voltage of 45 volts. And basically we took spectra around 400 hertz, 1, 2, 4, 10, and 20 kilohertz, and then measurements around the resonant frequency. And then this one, it's a little bit different because we sealed between each row of capsules, so they would act together and produce a higher resonant frequency. And you can see it's around 8 instead of 6 as unlike the previous one. And then this is done with stainless steel, and the stainless steel device had a lower resonant frequency than compared to the aluminum foil. And this is the individually encapsulated stainless steel, and this one's not really conclusive because it was really hard to work with, and I think some of the nanotubes might have been destroyed. And this one is assembled under argon, which increases the efficiency, and you can see that the resonant peak-to-peak voltage is much higher. It's almost 6 volts. And basically what we did is we assembled this one in the glove box under argon, and then so when we sealed it and took it out, like the inside working gas was still argon. So this is the theoretical maximum efficiency for different gases and different mediums. And this is based on the Carnot limit with the temperature gradient. In argon, you can heat the nanotubes to a much higher temperature, about 2000 Kelvin, theoretically. And then the maximum efficiency that can be attained is around 85%, though it's can't actually reach that limit. And then in summary, we created a flexible encapsulated multi-wall nanotube sheet sound projector, and we demonstrated its ability for sound generation. And these devices have different resonant frequencies, and at these resonant frequencies, there's a high power that's generated by the device. Also, the sound generation efficiency of the transducer that was produced in argon is much higher than the other devices in just air. And also, it's flexible and lightweight. Even after we bent it a lot, it's a fairly stable signal. And there are a variety of future applications using these flexible sound generators. And my future goal is I want to test these underwater because you can use them for sonar, you can use them for tracking, communication. And also I want to increase the efficiency of these devices without sacrificing power. And then, yes, these are some other applications, and actually one of them is a propulsion device that you can use with nanotubes. If you take a copper frame and you pull nanotubes over it and you seal it in a fixed volume container and apply a direct current, the nanotubes will heat up and create some pressure, but unfortunately I haven't been able to go that far with this. And yeah, I want to thank my mentor, Dr. Ali, and the NanoExplorers.